Welcome to Catalyst Conversations, the podcast that brings you real-world stories and solutions from a wide variety of acoustic experts. Each episode, we'll dive into a different topic from the world of acoustics, such as architectural and industrial noise control, seismic and vibration restraint, acoustical testing, or innovative design and engineering of sound control products. Our experts have decades of experience in this space and are eager to share their expertise with you. Join us in making the world a quieter place.
Hello and welcome to Catalyst Conversations. My name is Adam Ritzek and I am a content marketing manager at Catalyst, where I help to moderate our podcast discussions. Before we dive into this episode, we're excited to share a new event with you. Catalyst is hosting its first ever industry event this June in Texas. This free event is packed with value for attendees, where you can earn valuable continuing education units, gain insights into critical industry topics, connect with leaders from all the Catalyst brands, and enjoy fantastic networking opportunities along with great food, drinks, and activities. To learn more and secure your registration, please visit catalystacoustics.com/connect. We hope to see you there. Back to the focus of today's episode, where Eric Wolfram from Riverbank Acoustical Laboratories will lead this deep dive on the key concepts in building acoustics and how occupants experience each. Eric will cover several key topics in the space, including an explanation of the most common ASTM classifications cited in building codes and architectural specifications, insight into the physical properties of materials that contribute to real performance in each of these categories, and an introduction to the growing field of architectural acoustics. So now, we'll turn it over to Eric for this episode.
My name is Eric Wolfram. I'm the laboratory manager of Riverbank Acoustical Laboratories in Geneva, Illinois. And I also currently serve as the chair of the ASTM E33 committee, So this presentation is recorded in 2025, and by the end of 2025, I'll be term limited. So first, just a short explanation of what Riverbank Acoustical Laboratories is. We were founded in 1918, so over 100 years ago. The facility and lab operation was funded by this gentleman, George Fabian, and the lab chamber was designed by Wallace Clemens Sabin. We have a whole presentation on that history on our YouTube channel. So if you would like to go deep into our history, check that out. Today, we are accredited by NAVLAP as an ISO 17025 laboratory, and we perform about 26 different testing standards. We average about 1,200 tests per year for over 300 different organizations. So, however, most of our tests are ASTM C423, NRC, ASTM E90, STC, E492, which is IIC, and sound power testing. So the main goal today, the main thing I want you to walk away from this presentation with is an understanding of these three kind of basic concepts in building acoustics, what they mean and how they're tested, and what the test results mean relative to your experience of a building. So first, the first term is sound absorption. And when we use this term, sound absorption, we're referring to the ability of a material to reduce reverberation time within a space. Now, don't worry, I'm going to give you some good examples and deeper explanation on each of these topics. But just to start, remember, sound absorption is referring to the ability of materials to reduce sound reflections and reverberation within a space. Airborne sound insulation, or more specifically, sound transmission loss, is how we describe in building acoustics. It's how we describe the ability of a wall or barrier or window or door, or anything that's intended to block sound from one room through to the other. And then finally, impact sound transmission. And there are different ways this kind of test data can be used, but the standard had in mind when it was developed, and I think is still most frequently used around the issue of footfall noise in multifamily housing or hotels. So the question of how well do I hear someone walking on the floor above? So for each of these general properties of materials, ASTM has classifications. So for sound absorption, the classification that's most commonly used is noise reduction coefficient, or NRC. That's the rating you're most likely to see on things like acoustical ceiling tiles, wall panels, etc. For airborne sound insulation, again, the ability to block sound, you're going to see sound transmission class, or STC ratings. And then third, that reduction of footfall noise condition, you're going to see IIC ratings, or impact insulation class ratings. As you're beginning your journey in acoustics, it is intuitive that all of these things might be similar, and that the properties of materials that are good for one must be good for the other, right? And that they're somewhat interchangeable. Very wrong. So they're in some ways often opposite. Different types of materials are sometimes good with NRC and bad with STC, or may have a good STC but a poor IIC. This is common all over the place. So there is, from a physics point of view, there is some overlap, but it's really better to think of these as three completely isolated properties, three ratings which have nothing to do with each other. And if your question is in regards to STC, then NRC does not answer your question. So our lab, and labs in general, are built to control all sorts of properties and paths that sound might take to be able to identify these three classifications for a specific material. All right, so the first property that we'll look at in depth is sound absorption. And remember, this is a property of materials, or property related to interior of space. So it's the main consideration with sound absorption is reverberation. So one could think of, the sound absorption performance of a material as its ability to reduce reverberation. So what is reverberation? Well, within an enclosed space, hard surfaces will tend to reflect sound waves. Now, this diagram on the right here, this kind of gives like a simplified explanation of what's happening with a sound reflection. Now, generally, sound waves reflect off of a surface where the angle of incidence equals the angle of reflection. So they have sort of a predictable reflection pattern similar to, let's say, like a billiard ball, right? However, in reality, and we often in acoustics create these demonstrations with kind of focused sound waves coming out almost like a laser towards the wall, or a single line towards the wall. The reality is that sound waves are incredibly messy. And not only is the speaker creating very sound level at different positions around the speaker, which is all coming out in different directions, but those waves, as they propagate towards the wall, are constantly dispersing. So the sound is sort of flowing in all directions. So as all these sound waves are flowing towards the wall and reflecting in all directions, it creates this echo, right? This reverberation within the space. We measure that in terms of the reverberation time, which is generally the time it takes that sound field to decay 60 decibels after the source is interrupted. I'm going to give you a couple examples here of different spaces, or sounds recorded in different spaces, and how the room itself affects the sound. So believe it or not, in these first impulse sounds, this is the exact same device, the exact same noise source, recorded from the exact same distance, from the same microphone at the same level. The only thing that's changed is the room that this recording is made in. So this first recording will be of an impulsive sound in an anechoic or dead, we call it dead environment. Actually, that's not really an acoustics term, that's like an audio guy term, or audio person term. So I'll play it a couple times for you because it's real quick. So listen, you hear the metallic clarity and detail of this object. This is actually a 1950s pop gun that some of you have seen in our lab. And you hear like the very clear detail of the mechanism. All right, now we'll go to, again, same distance, same object, just only thing that's different is the room it's recorded in. So you hear, you lost all the detail of the mechanism, and you hear this long reverberant tail. This is, the recording was made in our room 0, our main diffuse field chamber. So this reverberation was very important to a space, especially like a critical listening space, but really any space where humans are occupying and talking and existing in. So in most cases, reverberation is like a type of noise. It's detrimental to the purpose of the space. Now I have to be careful because there are some very important counter examples to that, and which some of the acousticians are already shuffling in their seats saying, no, it's not. Okay, so something like a concert hall, especially a concert hall that is intended for choral music or orchestra, having a well-balanced reverberant sound field is very important to the musician performance and the experience of the listeners in that space. It's part of the experience. It's important. Even then, there's a limit, like not unlimited reverberation, and even the 6-second example is too long, but a good, well-balanced reverberation tail. Probably the upper end of the, if there's a spectrum of things that want reverberation versus don't want reverberation, I would say that on one end of the spectrum would be pipe organ music from like a cathedral or a classical worship space, and like Gregorian chant. Those would love a lot of reverberation. Now on the other end of the spectrum would be something like a movie theater, where you don't want this echo, and this echo would interfere with the purpose and function of that space. So this here is some speech recorded in a dead environment.
In order that hearing may be good in any auditorium, it is necessary that the sound should be sufficiently loud, that the simultaneous components of a complex sound should maintain their proper relative intensities, and that the successive sounds in rapidly moving articulation, either of speech or music, should be clear and distinct, free from each other and from extraneous noises. These three are the necessary, as they are the entirely sufficient, conditions for good hearing.
Now, same sound source, same distance, only thing that's changed is the room.
In order that hearing may be good in any auditorium, it is necessary that the sound should be sufficiently loud, that the simultaneous components of a complex sound should maintain their proper relative intensities, and that the successive sounds in rapidly moving articulation, either of speech or music.
So, in fact, I'm realizing I should have played it the other way around, because you have a clue. You already knew what the word said, but if you didn't know what the word said there, you'd have a real hard time making out speech. So that reverberation it's detrimental to your ability to understand speech in that environment. The field of acoustics, or building acoustics, started with this equation right here. This is the Wallace-Sabin equation. And this was developed by a gentleman named Wallace Sabin, and he was a professor at Harvard that derived this equation and basically started the whole field of architectural acoustics. It's a very simple equation, which allowed people at the time to predict reverberation time. And actually, this equation is still used today. It has its place and purpose in the field of acoustics today, although there are other alternative equations for other types of environments, and there are sophisticated acoustical modeling programs which will allow you to do more with more detail. However, the validity of this equation still holds. So basically, we're able to predict the reverberation time of a space knowing the air volume and the total sabins present in a room. Sabins is the unit of sound absorption. But what is a sabin? We have different ways of explaining this, and like a lot of physics metaphors, they can be very helpful, but also have their limits. And at the very high end of understanding, the metaphor is actually counter to understanding. So we'll try our best here. So I think that Wallace himself, and at least very early on, the explanation of a sabin was that one sabin was like 1 square foot of open window. This Wallace-Sabin equation is the basis for the ASTM C423 test method. So a variation of this equation, which is solved for the total sabins, and with a adjustment to correct for the speed of sound in that chamber, is used. So how we run this test is we will test the reverberation time in the empty space, and then we will install the material under test and then measure the reverberation times again. Using this equation, we're able to determine the total sabins of absorption in the empty chamber and the total sabins of absorption in the chamber when the material is installed. If you subtract the empty chamber, then you're left with a quantity of sabins attributed just to the sample under test. So a sound absorption area that has been added to the chamber just from adding this device or object or whatever it is under test. If the sample under test is a flat, two-dimensional material, then we can determine the sabins per square feet of that material. So in this example, we have an 8-foot by 9-foot rectangular patch of material, which is 72 square feet. So if we measured 72 sabins of sound absorption, and we have 72 square feet of material, then we would have 1 sabin per square foot. In architectural acoustics, we call that a sound absorption coefficient, so 1.0. Now, that term is not technically correct. It is not actually an energy absorption coefficient. However, that's the way, we have used that term in this industry. It's very traditional. So sound absorption coefficient. And for the most part, 1.0 is seen as 100% absorptive, but really what it means is you have 1 sabin per square foot. Now, if you have a sound absorption coefficient of 0.5, that's sometimes seen as being a 50% absorption, which is approximately correct. Where it breaks down is it is possible to achieve, it's actually possible and common to achieve rates of absorption greater than 1 sabin per square foot. So greater absorption coefficients greater than 1.0. And this is not alarming or anything like that. It's just the nature of the test. And maybe someday we'll do a presentation just on that subject. But yes, it's possible to have absorption coefficient greater than 1. So what is NRC? NRC is the classification or the single number rating for a test with a variable performance across different frequencies. So what that means is, this is an example of a test result for a sound absorption material. This is actually pretty good representation of, let's say, a 2-inch thick sound absorption core, something like that, just generally. And you see the performance is very different at different frequencies. So above 300 hertz, you're above 1.0 for most of the range above 300 hertz, but then the performance drops at lower frequencies. So it's harder to absorb lower frequencies generally. This is sort of complicated, right? And if you're marketing acoustical materials, you don't want to have to explain, well, our material has 0.45 at 160 hertz, and 1.1 at 1,000 hertz. You just want a single number that can be used in a broad way to compare material A to material B. So the traditional or historic rating for that single number was the noise reduction coefficient, or NRC. The definition of NRC is it is the average of the sound absorption coefficients at 250, 500, 1,000, and 2,000 hertz, rounded to the nearest 0.05. Now, some of you technical people may have some questions. Yes, so there are a number of problems with this, and this is not the way the industry would do things if it was to create a number today, a single number rating today. We have to remember this goes back to pre-computers, where everything had to be calculated by hand, and just a different understanding of when to round and how. Today, more recently, they developed a sound absorption average, or SAA. This takes a range of all the 1/3 octave bands from 200 to 2,500 and rounds to the nearest 0.01. At ASTM, we believe this is more technically correct, and it's also the currently defined single number rating. However, most of the industry still references NRC ratings pretty broadly. So what are the properties of material that contribute to sound absorption performance? Most sound absorption materials are porous or fibrous media. So that porosity and fibrous material is very important. So as sound flows through it, energy is lost as it moves through all that material, is lost in the pockets and all the different transfers of air to material to air. Thickness is very important for this type of absorber. So it takes about 2 inches of porous fibrous material of sufficient density to get an NRC of 1.0 with no airspace behind it. Density does matter, maybe less so than thickness, but density is important, and too much density can actually start to reduce performance as well. So there's a sweet spot, somewhere in the 5 to 8 or 9 pounds per cubic feet where materials are very effective. You'll often notice that some materials are installed with a deep airspace behind them. For example, acoustical ceiling tile. That airspace is a way to cheat, basically, in a good way, and get more performance out of a material than it should be allowed based on its thickness. And this is allowed. You are allowed to test with an airspace if the material is typically installed with an airspace. So for example, acoustical ceiling tiles, and there are a number of different mounting methods which define different types of airspaces, but they have a very significant impact on the performance of the material, and therefore the results are really specific to that mounting. The surface is very critical. That surface needs to be air permeable so that the sound waves flow through the surface and are absorbed by the core. Yes, so painting the surface of an acoustical wall panel, especially a very thick latex paint, multiple coats with a big woolen roller, yes, regardless of what anyone tells you, that will reduce the effective NRC rating. There are products out there that are tinted and painted by the manufacturer, and those companies put a lot of engineering into making that surface work well, so that when they test it, it is painted and coated and achieves the exact NRC. That's actually a difficult engineering problem for acoustical product manufacturers to get that just right. There's another category we won't go into too much, which would be like Toon's diaphragm absorbers. So it is possible to make a sound absorber that has a resonance. Typically, these are effective at certain frequencies, though, and not broadband. Next up, sound transmission loss. This is, again, referring to the ability of walls to block sound. Sound transmission loss measures how well a wall will prevent you from hearing your neighbor through that wall in a condominium. So airborne sounds, human voice, television, a dog barking, these sorts of things we would consider airborne sound. So what are the properties of a material that generally give higher sound transmission loss or a better ability to block airborne sounds? Most fundamentally is mass. So generally, in almost all very broadly, heavier is generally better. So heavier materials are more massive, and therefore it takes more energy to make them move or to make them vibrate. Limpness, so this one's often counterintuitive, and we'll hit on this in a couple of different ways. But stiffness works against you generally for sound transmission loss. So stiffness is not your friend for sound transmission loss generally. And if you think about it, lead is kind of a classic legendary material used in recording studios from the mid-century on creating sound isolation. And lead, what does lead have? It's very massive, very heavy, and it's also very limp. So it was sort of a perfect ideal material. Now, for various reasons, people work with lead much less than they did, in the 1950s. So further, air tightness, small gaps will kill your STC performance much more than you might think. A good example I give of this is, so you're in your car, you're driving in your car on the highway. If you open your window all the way open, you hear all the air turbulence noise and tire noise and everyone's engine and everything just coming clear through the window, right? If you close that window halfway, it sounds almost the same, right? 3/4, okay, now you may have noticed some change, but it's still very loud. 7/8, still very loud. It is only when the window fully seals into the top of the door, into the seal, where you get that kind of almost airtight seal, that's when the sound sucks away and is gone, right? So you had to achieve that airtightness in the window to achieve the maximum possible STC out of that window. Next up, damping. This is important. This is a critical factor of how the wall is performing. It's not always thought of in as much detail as the others, but this is basically friction in the vibrating system, whatever it is. So basically dissipating energy in that vibrating system. And then finally, cavity absorption. So if you think of this acoustic guitar, the effect of that wood body on the guitar, and when the string is played, is that it kind of amplifies or it resonates in a way that brings that energy, enhances the sound, right? You don't want that. You do want that with a guitar, but you don't want that with a wall assembly. So imagine if you stuffed the body of that acoustic guitar with fiberglass or mineral fiber insulation, then played it, it would be totally dead. You probably barely hear the strings, right? So that's basically what absorption does within a wall cavity. It reduces the resonance of that hollow cavity in the wall. So it's very important to note that STC is a system performance and not a material performance. What we mean is you don't have an STC rating for each of the components of a wall. You have an STC rating for the sum total of the wall or the window or any other acoustic system. So when you're thinking about systems or wall systems or doors or windows for sound transmission loss for STC, you want your system to be more like the 1970s Cadillac, which was heavy, floating, and airtight. So the isolated suspension keeps the vibration of the road out of the body of the vehicle, soft floating suspension, and a really massive vehicle that took a lot of energy to make move. And then airtight and closed cabin, which kind of blocked out the outside world, right? So that's the way you want to think for wall assembly. You want your wall assembly to be more like the Cadillac and not like the go-kart, right? The go-kart is very, very light, very stiff, and open. So what does this mean for the wall assembly? Generally, more layers is better. Adding mass of the gypsum board will improve generally up to a point the performance of the wall assembly. And there are certain materials that are made to be lightweight. Consider that that lightweight alternative may affect your STC rating. Stiffness is, again, very critical as well. So, and sometimes counterintuitive. So lighter or thinner steel is actually better for STC. So think of it as the steel is lighter, it's more flexible, and the very light gauge steel is almost like a resilient. It's, if you hold it, you can almost crush it in your hand. It's very resilient on the very light gauge steel. And then on the other end of the spectrum, maybe let's say like a 2x4 wood stud is very, very rigid, right? Very stiff. So the same gypsum board on both sides, the same insulation in the cavity, and the same spacing and fasteners, you could, or I should say, tighter spacing and tighter screw pattern could range from STC 50 on a single layer gypsum board wall with really favorable framing conditions down to STC 36, 37 on the same gypsum board, the same materials, but more rigid framing. So again, wider stud spacing is generally better for STC. So like 24 inches on center will generally perform better than 16 inches on center. And then a wider fastener spacing will generally perform better for STC. So tighter screws pattern, you know, the contractor may think they're doing an extra good job because the wall is really important. We're going to put a lot more screws in. That actually can hurt your STC very significantly sometimes. So now some of you are already thinking, okay, this is a problem because all the things we just mentioned are not possible in my building because we need that wall to be structural and we need it to pass fire requirements. Well, the good news is that when your wall needs to be stiff for those reasons, there are other alternative products that are able to reintroduce that flexibility underneath the gypsum board. And that's where like resilient channel or isolation clips come up. So again, a single layer 5/8 type X gypsum board on both sides of a stud wall with the same insulation in the cavity, that could range from STC 37 to STC 50, just depending on these factors. So, and then finally, air tightness. In the lab, we will caulk the track to the test frame so that there's no path of leakage around the test frame. And then after the gypsum board is installed, we isolate the gypsum board a small amount from the test frame, and then we fill that with a flexible airtight mastic seal all the way around both sides. So in the lab tests, we intend to eliminate that flanking around the sample or through the test apparatus so that the sample can perform at its best. But in the field, you want to consider that as well. And then finally, cavity absorption. We want to make sure that this is not a hollow cavity that will resonate. I have to be careful how I say this one, but you know, the properties we talked about with sound absorbing materials apply in this cavity here. And you want to avoid materials that are very, very rigid to the point where they're increasing the stiffness of this wall and not adding much mass. So think about that. So materials that might be stiffening the wall and not adding much mass, those could actually hurt your STC rating. So, and then finally, damping. There's a way to introduce more friction in the vibration of these materials. So this would be something like the viscoelastic damping compounds or the quiet gypsum board products that are out there. These are real materials. They have real benefits. They're a good tool in the toolbox. So I'll tell you a little bit about how we run this test. We have a special set of chambers that's built where we have 2 reverberation chambers that are joined by an aperture. In this case, room 1 might serve as our source room. So we're generating about 110 decibels, 120 decibels of pink noise in that room. I mean, imagine that you're standing at the bottom of Niagara Falls inside of a cathedral. That's what it sounds like in that chamber. You don't want to be in there. And then we measure this average sound level, spatial and time average in that chamber. And then we make that another measurement on the other side of that chamber. And then we correct for the area of the sample and the presence of sound absorption in the receive room. There's also an ambient noise correction, but that's in a lab condition, that's almost negligible. So that process tells us that all the sound that we're measuring in this receive room is coming through the sample because we've isolated all other paths that sound could take around it. And the sound level, the reduction through that sample of that size is determined there using this equation here. So the transmission loss is the source level minus the receive level with that correction I mentioned before for area and sound absorption. All right, finally, impact sound transmission. Now I have to tell you, this is probably the most, this topic is, I've seen more grown men crying in my life about anything, about this topic than about anything else. So imagine that you bought your dream condominium. You spent $2 million on this condominium and you move in and very quickly realize that you hear every single footstep, tap, 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 back and forth all day long in the ceiling above. You hear every footstep from the person walking above you all day long. Now, acoustics sometimes seems like it's not that big of a deal, or less important than, let's say, having the right kitchen cabinets and countertop. But when you have that situation and you're very noise sensitive, you don't care what your countertops were made of. That is the #1 problem in your entire life. And there are really no easy solutions here. So we encourage, whenever possible, that this consideration is made when a building is built and or when floor coverings are being installed, so that, that you do it right the first time. How do we test this? So in the very early days, I think like 1950s, let's say, the method would be they would have a woman in high heel shoes walk in a figure-8 pattern on the floor and make measurements below that, and try to standardize the gait and the speed and all that stuff. So this is problematic for a lot of reasons, right? So they came up with this machine. This is a standard tapping machine, and this is what we use in our IIC and field tests, our AIIC tests in the field, so E492 and E107. So this machine has a series of metal hammers, which are all dropped from a defined height, and this sequence happens at a defined speed. And it's basically like almost like an inline 5 engine. It's constantly tapping on the floor, and it's loud, but it creates this kind of controlled standard impact noise function into the floor assembly. We'll take that machine and place it on the top of a floor ceiling assembly, and then we make measurements in the room below. So the source room and receive room is below. There's also, similar to E90, there's corrections for the sound absorption and ambient noise in the receive room. So what are the properties of materials that will contribute to its impact sound isolation or its IIC rating? So maybe in my opinion, one of the most critical factors is that flexibility on the surface. So if you go back to, the 70s and 80s in multifamily housing, you almost always had carpeted floors in apartments. And this is why it was not as much of a hot topic back then, because that carpeting does a really good job of preventing the footfall noise from getting into the structure, into the subfloor structure. It eliminates that strike at the first possible position. So that surface is very critical. However, we know that the modern homeowner, modern consumer would rather saw off their own arm than have a carpeted living room, right? I get it. So the hard surface flooring options like tile and wood and laminate, they just are inherently worse for IIC performance. And so you want to take special consideration on isolating these floors. Again, generally, it's better if you can get that isolation to happen further up in the structure. So also mass is also critical, and the presence of generally a suspended ceiling in general is also very important. That's another trend, as the demand for higher ceilings in condominiums is counter to the interest of the acoustics. So exposed slab configurations where you look up from the room below and you see the actual concrete subfloor without anything suspended, that's important to take consideration in acoustic performance. As we mentioned before, the IIC rating, and this is really critical to hammer in on IIC performance. IIC is not a materials rating. IIC is not a rating on an underlayment or a floor covering. IIC is a rating on the entire subfloor, of which that floor covering or underlayment is one component. So you have, you will sometimes see, maybe if you go into the big box store, you might see an underlayment with a label on it that says IIC 74, let's say. So the question one should ask is, well, okay, what was the assembly that was tested? Because this IIC 74 doesn't tell me anything. In fact, it's a clue that it was probably a pretty substantial assembly. So you'll want to look at the laboratory test report, which will give you specifications for exactly what was tested, including the finished floor, underlayment, subfloor, suspended ceiling, any isolators that were in place, insulation in the cavity, basically the whole buildup. This is very important. So, like I said, with floor ceiling assemblies, especially, you really want a lab test report to verify that before you pay to have a flooring installed or you build a building, that you know that you're going to have a satisfactory performance. We do a lot of different tests on a lot of different floor, finished floors, underlayments, suspended ceiling systems. The base slab by itself gets a STC 56, which is good news, right? So that tells you you pass the minimum building code. We'll get to that in a minute on what that is. But you pass that with just the slab. That's because even though the slab is very stiff, there is a lot of mass here. So, and that is really doing the work on the airborne sound transmission. However, even though you get STC for free, IIC is a big consideration. So without any consideration, without any floor covering, you would have an IIC of 27. So if you had a polished concrete floor and an exposed slab on the room below, that's a very poor IIC performance, 27. So what do you want to look for? Like I mentioned, you want to ask for an acoustical lab test report. And lab test report, it's usually not a 1-page or 2-page document. It has a number of things. So I'll quickly go through what to look for in a lab test report. So obviously the testing agency who performed the test. how are they qualified to perform the test? So in our case, we're accredited by NAVLAP, which is the U.S. federal government's accreditation agency. There are other accreditations as well, but you want to make sure that that this is a lab that's accredited to perform as a lab as well as to perform this test. We'll mention in this first paragraph here what the standards were that were followed to perform the test. We will tell you when the test was performed. The information provided by sponsors section. So starting with 2017, the 2017 version of ISO 17025, they required labs to separate information that's provided by the sponsor versus information that's directly observed by the lab, which is really smart. So we have a section for sponsor provided information, as well as a section for our own observations. And then most of our modern test reports starting around 2012 and later will have photos of the sample. And I don't know about you, but for me, it's a lot easier to figure out what's going on in a build by looking at photos than reading paragraphs. So we'll also provide 1/3 octave band results, the single number rating, and you'll also have a certified signature on every report. So once you authenticate this signature once, I believe that anytime you see a future report from me, IdenTrust will validate that signature when you open the PDF. These ratings, the airborne and impact sound rating, STC and IIC, are referenced in the International Building Code for multifamily housing. So for airborne sound insulation, they want not less than STC 50, or if it's field tested, not less than NNIC 45, which is the field test, sort of not equivalent, but the field test version of E90, which is E336. Now, one might think, well, we should try to just do the field test because that's easier to pass than the lab test. Actually, that's not true. Oftentimes, a field test can be more challenging because there's a lot of factors that you can't control that could be influencing the test results. And we are seeing more and more where developers are being asked to provide both the lab test prior to construction and then the field test validation afterwards. So, and then impact sound insulation, IIC 50, and similarly, they allow 5 points flexibility for the NISR, which is the field alternative. So it should be noted that these ratings, STC 50 and IIC 50, even though this is the building code requirement, this should really be seen as a minimum acceptable performance for multifamily housing. So this is not soundproof, this is not high quality, this is, we did the minimum and we got STC 50. Luxury, might be in the range of STC 65, 60 if you can, or 60, 65 if you can get it. And then 55 to 60 might be a good, reasonable target for, high quality condominiums. So, but there are a lot of different considerations there and a lot that goes into designing for that. So in our experience, most of the time when there are really significant complaints, it's around this level or slightly lower. Oftentimes the worst case scenario is someone, does a field test and they get NNIC 45 and they're not happy with it, but it passes the building code and that's that. So just a consideration. So anyone that's designing buildings to try to shoot for higher than these. And where can you find information on these test reports? I'm going to share a couple examples for you that I really like. Probably in my experience, like one of the best comprehensive directories of wall assemblies and floors is this USG Design Studio. They give fire ratings and STC ratings for all different types of assemblies, and I really like this layout. There's also the GA600, which provides a big list of acoustical and fire performance for different systems. And then product manufacturers will often make our test reports available on their websites. And if you see numbers and you're being held accountable for the acoustic performance of the building, I recommend reaching out to the technical support of the manufacturer and ask them, for that test report. Clark Dietrich is another one. I really like the way they lay out their test results and for all their different products and systems. We also perform field testing as well. In the lab, we have perfect conditions. We control for all variables and eliminate flanking paths, but then field environments are often not ideal. So when to do lab tests versus field? So lab tests are performed on products and systems before the sale and installation, and field tests are performed on building systems after the building is built. So one thing to remember, whenever you hear these ratings, STC, NRC, IIC, these are all lab test results. So these are not field tests. There are field tests that are similar, but they have different classifications. So an acoustic requirement for an STC rating is asking you for a lab test. And that typically is sponsored by the product manufacturer, although we're seeing more and more, mock-ups for a specific building, project-specific mock-ups. When you're involved in the construction of a building, the acoustical considerations are very important, and we talked about, where things can go sideways and all that complexity, and then balancing that out with the structural and fire requirements, which even us acousticians will say, yeah, fire is directly a life safety issue. You should not compromise your fire performance. So that's one of the things that an acoustical consultant will do on your project is help to work with those various trades to ensure a good outcome. So there's a trade organization for acoustical consultants, the NCAC, and they have a directory, and you can most likely find someone in your area that's qualified to consult on the project. Another credential that I think this might be the most well-respected credential in the trade of acoustical consultants or acoustical engineering. This would be the INCE board certification. And there's a directory on INCE USA website which can find board certified engineers in your directory. When you're dealing with really technical noise control engineering, I definitely recommend taking a look at this directory. And finally, in review, sound absorption is classified by the noise reduction coefficient, or NRC rating. NRC is specifically related to the behavior of sound within a space, so echo and reverberation, sound reflections. Sound transmission class, STC, this is specifically related to airborne sound transmission through a wall. And then impact insulation class, this is related to the footfall noise that you hear in the floor ceiling assembly above you.
Thank you for listening to today's episode, and please be sure to subscribe to Catalyst Conversations. If you've been enjoying these discussions, we'd appreciate if you could leave us a review to help others in the industry learn more about our podcast. And as a reminder from earlier, register for Catalyst Connect this June in Texas. To learn more and secure your spot, visit catalystacoustics.com/connect. Thanks again for listening, and stay tuned for more episodes as we continue to explore noise and sound control advancements shaping the future of industries worldwide.